Okay, so we're now going to continue our discussion of this, and I want to discuss this equation a bit more. Firstly, I want to rewrite it a little bit, because this index here, I, appears twice, and in both cases it's a dummy index. So just to avoid confusion, we'll replace it with another index. So I'm just going to replace the first index with, shall we use the index u. It's a dummy index. All it means is sum over u, so you can take on every value 1 to 2 in this case, because it's just a two-dimensional manifold. But if we were doing this in 4 dimensions, you'd obviously have to go over 1, 2, 3, 4, and you'd have to sum over each of them. So I'm going to write it out explicitly what this equation actually says, because it's a little bit easy to get lost in the abstract tensor notation here. So all this is saying is that I'm going to write it out in full normal differential notation. So it varies. There are two equations. The first reason the reason for that is because there is a free index here. J is a free index. So this is really the zero vector. It's 0 twice for each value of j. So it's 0 when j is equal to 1, and it's 0 again when j is equal to 2. So what this is really saying is that, so we'll take this bit first. So del y, we'll do j is equal to 1 first. So this is two equations basically. Del y1, then we've got del x. Now u is a dummy variable, so you have to sum over. So we get 1 x double dot 1 plus del y1 del x 2, and we're now just putting in the second of these, 2. So that's that term done now, because we've only thankfully done it in 2 dimensions. But if you were doing this in 4 dimensions, you'd have to continue on and do the third one and the fourth one. But we're going to go on to the next one over here. So j is again equal to 1, and now we've got to sum over both of these. So we'll start with both I and p is equal to 1. Then we'll do I is equal to 1, p is equal to 2. Then I is equal to 2, p is equal to 1. And then I is equal to 2, p is equal to 2. So we get the second derivative of y, 1, with respect to x1, so x, I could have done that as dx1 squared, but never mind, x dot 1, x dot 1. And then we're going to, now, to avoid me having to write it out twice, actually no, I'll just write it out twice, just to keep it nice and simple. So the next one is 1, dx, we'll make I1 and take p to 2, x dot 1, x dot 2, then we'll get plus d2y1, dx2, dx1, x dot 2, x dot 1, plus d2y1, dx2, dx2, x dot 2, x dot 2 is equal to 0. So that's one of our differential equations. We now have another one, which I'm not going to write out, but all you do is you replace all the places where j was with a 2. So you replace 2 here, 2 here, 2 here, 2 here, 2 here, and 2 here, and you get a second differential equation. And what we've got there is a system of differential equations, and the function that we're trying to solve for is x1 as a function of s and x2 as a function of s. And all over the place we've got second derivatives of these functions. So whenever we've got x dot dot 1, that means the second derivative of x1 with respect to s squared, ds squared. And whenever we've got x dot 1, that just means dx1 dxs. ds. So we've got a very complicated system of differential equations, but fundamentally we've only got two functions to solve for, and we've got two equations, two differential equations, this one and the corresponding one with j is equal to 2. So in principle we can solve that system of equations. So we can solve, if you give me these functions here, which we're going to look at how you actually get those in a moment. But if you give me these functions, functions as a function of, generally it's going to be as a function of x1 and x2. So y was a function, y1 and y2 were both functions of x1 and x2. So you can, in principle, if you knew these functions, you can calculate all these derivatives. So we're going to work out how to actually find these, and we're going to work out how to do it without actually finding those. But for now, you can just think of we have to know this coordinate system, and then we could work out all of these, and then what we could do is we could solve that differential equation, in principle at least, and get these two functions, and then what we've got is our complete trajectory of the particle through our space. So we solve the problem, basically.